Congruence relation defined on the set of integers. When do we say that two integers are congruent? Two integers, say a and b, are said to be congruent to each other modulo a positive integer m if the difference a minus b is divisible by m. That is, if the difference a minus b is a multiple of m. We can express this relation as a congruent to b modulo m. We can also say that m divides a minus b when a is congruent to b modulo m. Let's consider some basic properties of this relation. First relation is a is congruent to a modulo m. That is, we claim that the relation is reflexive. Proof: we know that a minus a is equal to 0, which can also be expressed as a multiple of m. That implies that m divides the difference a minus a, which means that a is congruent to a itself. Next property is a congruent to b modulo m if and only if b is congruent to a modulo m, which means that the relation is symmetric. It can also be easily proved from our definition. A congruent to b implies that m divides a minus b, or that a minus b is a multiple of m, which also is possible if and only if b minus a is also a multiple of m. That is, if and only if m divides b minus a, hence b is congruent to a modulo m. So the relation is symmetric. Now next relation we consider is the transitivity of the relation. That is, a congruent to b and b congruent to c implies that a is congruent to c. A congruent to b and b congruent to c implies that both a minus b and b minus c are multiples of m, so that a minus c can be expressed as the sum of a minus b and b minus c, which implies that a minus c is a multiple of m. That is, m divides a minus c, so that a is congruent to c modulo m. These properties imply that the relation congruence modulo m is an equivalence relation, since it is reflexive, symmetric and transitive. Since congruence modulo m is an equivalence relation, the set of integers, that is, the set in which our relation is defined, will be partitioned into equivalence classes. Equivalence classes are a collection of sets which are mutually disjoint, and their union will be equal to the set in which the relation is defined. In our case, the set is Z. For a fixed integer m, each equivalence class with respect to congruence modulo m has one and only one representative between 0 and m minus 1. Each integer will be belonging to exactly one equivalence class. For example, class of 0 will be the collection of all integers which are related to 0, that is, the collection of all integers which are congruent to 0 modulo m, or in other words, this will be the collection of all multiples of m. Similarly, class of 1 will be the collection of all integers which are congruent to 1 modulo m, that is, the collection of integers of the form a multiple of m plus 1. Similarly, we can observe that collection of class of 2 will be the collection of all integers of the form and in a multiple of m plus 2. Class of 3 will contain all those integers of the form a multiple of m plus 3, and so on. Class of m minus 1 also can be expressed like this. Now we can observe that class of m will be equal to class of 0 and class of m plus 1 will be equal to class of 1 and so on. Thus, the distinct equivalence classes are class of 0, class of 1, etc., class of m minus 1. These are called congruence classes modulo m. Every integer belongs to exactly one congruence class, since the congruence classes are the equivalence classes with respect to our relation. Now, if we consider the set 0, 1, 2, etc. m minus 1, this set contains exactly one representative from each equivalence class. This set is also the set of all possible remainders obtained when an integer is divided by m. So, this set is called the set of least non-negative residues modulo m. Similarly, a set of integers, say set r1, r2, etc., rm, set in which every integer is congruent to exactly one element of this set modulo m, is called a complete residue system modulo m. So, if we take any integer, say n, then n will be congruent to exactly one element from this set. And we can also observe that this set contains exactly m integers, and if we take any two members of this set, they won't be related to each other. So it is easy to observe that our set 0, 1, 2, etc. m minus 1, that is the set of least non-negative residues modulo m. This set is also a complete residue system modulo m. Hence, the set of least non-negative residues modulo m is the collection set 0, 1, 2, etc. m minus 1, and a complete residue system modulo m is a set of m integers in which no two members are related to each other. The set of congruence classes can be denoted by the symbol z by mz, which contains the elements class of 0, class of 1 and so on, class of m minus 1. We can observe that this set together with addition modulo m and multiplication modulo m will be a ring, and this ring is called the ring of integers modulo m. Since the set 0, etc. m minus 1 is the least residue system modulo m, then every integer n has a representative in the ring of integers modulo m. So we can find a j such that n belongs to class of j. Then n will be congruent to j modulo m, and j will be a member of the set 0, 1, etc. m minus 1. This ring of integers modulo m plays an important role in many cryptographic applications.